Hello, my name is Kirk Hochstetter, and today I will be presenting to you about the mechanical properties of materials. In today's presentation, we will start with a quick review of stress and strain as they're applied to structural members. From there, we can better understand the mechanical behaviors of materials through an examination of stress-strain diagrams and how the different types of materials react differently in compression and tension. Understanding today's materials is fundamental to your ability to design structures and machines as we learn about the mechanical behaviors of the material being used. This is not only relevant to new designs of structures and machines, but also how we repair existing systems where replacement costs and schedule impacts can be prohibitive to the bottom line of the project, but also the ability for the facility to continue to operate and create revenue. Before we jump into the mechanical properties of material, let's quickly review the most fundamental concepts of the mechanics of materials, stress and strain. The principal objective of mechanics of materials is to determine the stresses, strains, and displacements in the structures and their components due to the loads acting on them. Remembering that stress is the force that is applied to a unit of area and that strain is the displacement that occurs to the material due to the stress, the figure helps us visualize how this looks in application. Example on the left represents how a rod under tension stress is stretched to a length of delta L when a force is applied parallel to its length. Conversely, example B on the right shows the same rod compressed by forces with the same magnitude in the opposite direction. For very small deformations, the uniform materials delta L is approximately the same for the same magnitude of tension or compression. For larger deformations, the cross-section area changes as the rod is compressed and or stretched. Assuming that the stresses are uniformly distributed over a cross-section, we will see that the resultant must be equal to the intensity times the cross-sectional area, cross-section material under force. Understanding this, we can use the following expression for the magnitude of the stresses. Sigma equals P, the force being applied, divided by the cross-section of the area where it is applied. The strain of the material can also be calculated and represented as the elongation per unit, represented by the Greek letter epsilon and given by this equation. When we measure the change in length and divide it by the original length, we can express elongation per unit, epsilon, as a percentage change with positive values being associated with tensile strain and negative values representing compressive strain. Taking what we understand about how we calculate stresses and strains, we can begin to plot this information to better understand the properties of our materials. The two typical tests that help us understand this are the tensile and compression tests. In these tests, measuring devices record the deformations as the machine subject the test specimens to forces of tension or compression. Using automatic control and data processing systems, the machines will tabulate and graph the results. The tabulation and graphical representation of these test results can be seen on the right of this slide. This is a typical stress-strain diagram for structural steel, and we will use this graph to help understand the mechanical properties of materials. The sigma axis represents the stress that is applied to the test specimen and identifies the proportional limit, yield stress, and ultimate stress. The epsilon axis represents the strain that occurs with the test specimen and identifies regions including the perfect plasticity of yielding, strain hardening, and necking that has occurred. When we examine this diagram, we see that we have a straight line from the origin to the point A. This region is not only linear, but also proportional. Beyond point A, the proportionality no longer exists, and we call this point on the sigma axis representing stress as the proportional limit. Along the epsilon axis representing the strain, we call this the linear region. The slope of the straight line created by these two measurements is called the modulus of elasticity that we will discuss later in a future lesson. With an increase in stress beyond the proportional limit, the strain begins to increase more rapidly for each increment in stress. Consequently, the stress-strain curve has a similar and smaller slope until at point B, which is called the yield point. Beginning at point B, the curve becomes horizontal and considerable elongation of the test specimen occurs with no noticeable increase in the tensile force from B to C. This phenomenon is known as yielding of the material, and the compressive stress is known as the yield stress of the steel. This horizontal section from B to C, the material becomes perfectly plastic, which means that it deforms without an increase in the applied load. The elongation of the mild steel specimen in the perfectly plastic region is typically 10 to 15 times the elongation that occurs in the linear region. After undergoing the large strain that occurs during yielding in the region BC, the steel begins to strain harden. During strain hardening, the material undergoes changes in its crystalline structure, resulting in increased resistance of the material to further deformation. Elongation of the test specimen in this region requires an increase in the tensile load, and therefore the stress-strain diagram has a positive slope from C to D. The load eventually reaches its maximum value, and the corresponding stress at point D is called the ultimate stress. Further stretching of the bar is accompanied by a reduction in the load, and fracture finally occurs at a point such as E. Near the ultimate stress, the reduction in the area of the bar becomes clearly visible and pronounced necking of the bar occurs. In this slide, we can see how necking of the mild steel bar occurs in tension and how the reduction in area decreases. Once the area has been reduced so that the load cannot be carried by the bar, a fracture will occur and we find our failure point. With this understanding of how structural steel will perform over a stress-strain diagram, it is important to understand that this is not the same for other materials. We can start to catalog these groups into metallic and non-metallic materials. We just witnessed how structural steel performed with increases in tensile forces, and we will find similar characteristics with other metallic materials such as iron, copper, aluminum. With non-metallic materials such as concrete, wood, glass, plastic, rubber, and brick, we will discover that their differing characteristics impact their performance under similar testing conditions. Historically, metals have been more important than non-metallic, but composite materials such as engineered plastics and advanced ceramics have recently increased in importance. While metallic and non-metallic materials have been able to meet the requirements for design, ultimately, decision-making of materials will come down to cost as well as environmental impact, energy requirements, recyclability, life cycle costs, and even an aesthetic value. Metals such as structural steel that undergo large permanent strains before failure are classified as ductile. For instance, ductility is the property that enables a bar of steel to be bent into circular arc and drawn into wire without breaking. Non-metallic materials such as rubber maintains a linear relationship between stress and strain up to relatively large strains as compared to metals. Beyond the proportional limit, the behavior depends upon this type of rubber, as some kinds of soft rubbers will stretch enormously without failure. Materials that fail in tension at relatively low values of strain are classified as brittle. Examples are concrete, stone, cast iron, glass, ceramics, and a variety of metallic alloys. Brittle materials fail with only little elongation after the proportional limit is exceeded. Also, a loaded plastic may stretch gradually over time until it is no longer serviceable. For example, a bar of polyvinyl chloride subjected to a tensile load that initially produces a strain of 0.005 of an inch may have that strain doubled after 1 week, even though the load remains constant. This phenomenon is known as creep, which we will discuss in upcoming sections. Stress strain curves for materials in compression differ from those in tension. Ductile materials such as steel, aluminum, and copper have proportional limits in compression very close to those in tension, and the initial regions of their compressive and tensile stress strain diagrams are about the same. However, after yielding begins, the behavior is quite different. When the material is compressed, it bulges outward on the sides and becomes barrel-shaped because friction between the specimen and the end plates prevents lateral expansion. With increasing the load, the specimen is flattened out and offers greatly increased resistance to further shortening. Brittle materials loaded in compression typically have an initial linear region followed by a region in which the shortening increases at a slightly higher rate than does the load. The stress strain curves for compression and tension often have similar shapes, but the ultimate stresses in compression are much higher than those in tension. And unlike ductile materials, which flatten out when compressed, brittle materials actually break at the maximum load. Throughout this presentation on the mechanical properties of materials, the information that has been shared has been used to show you how different materials perform under tension and compression. From here, we build on this knowledge that will ultimately culminate in your ability to make decisions on what materials should be selected for their unique designs. Part of this decision-making will be engaging with the manufacturers or suppliers of the material you plan to use so you have accurate information when selecting the elements. Additionally, we will build on this knowledge in upcoming sections so you can understand how elasticity, plasticity, and creep, and how materials react when they are unloaded. Thank you for your time, and I look forward to building on this knowledge in our next section, elasticity, plasticity, and creep.